Ball lightning. Across centuries and continents, people have reported glowing spheres of light dancing through stormy skies. These mysterious orbs, known as ball lightning, appear during or after ordinary lightning strikes. Witnesses describe tennis ball-sized balls that glow red, orange, white, or blue, sometimes hovering near the ground, drifting through windows, or vanishing with a soft pop. Despite detailed reports, scientists still struggle to explain exactly what ball lightning is or how it forms. Historical accounts of ball lightning date back at least to the 1600s. One famous observation came from the British scientist Robert Boyle, who in 1675 described a ball of fire that moved along the ground after a thunderclap. Sailors, farmers, and city dwellers all told tales of glowing spheres rolling across fields or bouncing around rooms during storms. Some reports speak of balls that left scorch marks on walls, melted metal, or gave off a sulfurous smell. Yet others vanished silently, leaving only awe and confusion behind. The main challenge is that ball lightning is rare and unpredictable. Unlike cloud-to-ground lightning, which we can study with sensors and high-speed cameras, ball lightning appears spontaneously and disappears in seconds. For centuries, researchers had only eyewitness accounts to rely on, valuable but hard to verify. Descriptions vary widely. Some balls move slowly and steadily, others dart or zigzag. Some grow in size, some split into smaller spheres, some explode, others simply fade away. No two sightings are exactly alike. In the laboratory, scientists have tried to reproduce ball lightning under controlled conditions. Beginning in the 1960s, researchers created glowing plasma balls by vaporizing silicon in an electric furnace. The hot silicon vapor formed tiny particles that glowed as they cooled, resembling small fireballs. Other experiments used high-voltage discharges in water droplets or special gases to generate luminous spheres. These lab plasmoids lasted only fractions of a second, far shorter than many real-world accounts, but offered a glimpse into possible mechanisms. Several theories compete to explain ball lightning. One model treats it as a self-contained plasma, a hot, ionized gas held together by magnetic and electric fields in a spherical shell. In this view, a lightning strike creates a burst of radio frequency energy that becomes trapped in a plasma bubble, sustaining its glow for a moment. Another idea suggests that ball lightning forms when lightning vaporizes ground materials, like silicon oxide in soil. The vapor cools and condenses into nanoparticles that burn, producing a glowing shell that drifts on air currents. A third theory invokes microwave resonance. Lightning may generate powerful microwave pulses that, under rare conditions, bounce between water droplets in a cloud or the ground and form a standing wave pattern. In this cavity, microwaves heat the air and create glowing plasma balls. This model can reproduce some ball lightning behaviors in microwave ovens, but it struggles to match larger, longer-lasting sightings. Despite these advances, no single theory covers every detail. Some eyewitnesses report balls that pass through glass without breaking it. Others describe balls that move against wind or through rain. Temperature estimates also vary. Some observers say the orbs feel cool to the touch. Others claim intense heat. Measuring these properties in real time remains nearly impossible. In recent years, a few fortunate researchers have captured possible ball lightning events on high-speed video. One clip from China shows a glowing sphere moving along a power line before disappearing. Spectral data hints at hot ionized gases at several thousand degrees, but the footage is too brief for definitive conclusions. Still, each recorded sighting brings science one step closer to understanding. Ball lightning challenges our assumptions about how electricity and matter interact in nature. It reminds us that storms harbor surprises beyond the flash and crash of lightning bolts. For engineers, studying ball lightning could improve our designs for high-voltage systems and lightning protection. For physicists, it offers a window into complex plasma dynamics and energy confinement. The Socorro UFO. On the evening of April 24th, 1964, in the small town of Socorro, New Mexico, police officer Lonnie Zamora found himself chasing reports of a speeding car on a quiet highway. As he rounded a curve, he spotted something unexpected: a gleaming, egg-shaped craft, about the size of a small car, resting on four skinny legs in an open field. The object was painted a silvery white and drew Zamora closer with a strange, low, humming sound. Zamora, a careful and clear-headed officer with years of experience, watched as two small figures in white coveralls stood near the craft. He described them as no more than 3 feet tall, with arms dangling at their sides. The figures did not speak or move toward him. They appeared as curious about him as he was about them. His radio crackled with a faint roar, and the ground vibrated gently under his feet. As Zamora approached, the craft suddenly lifted off with a roar and a flash of blue-orange flame. It rose vertically, hovered for a moment, then shot away at high speed toward the north. Zamora felt intense heat on his face from the exhaust. He called dispatch with a shaky voice, reporting the craft's unusual shape and the two figures. Within minutes, sheriff's deputies and curious neighbors arrived, drawn by the sound and Zamora's urgent call. Investigators from the U.S. Air Force's Project Blue Book arrived to examine the scene. They found 4 shallow impressions in the hard-packed ground, each about 6 inches deep and arranged in a rough triangle. Nearby, patches of grass and small shrubs showed signs of scorching and flattening. On the road leading to the field, witnesses reported skid marks and traces of white ash. Soil samples tested by the Air Force showed only minor changes in chemical composition, but nothing conclusive. Despite the physical evidence and multiple witness statements, the Air Force labeled the incident unknown, a rare rating in Project Blue Book's files. Most UFO reports received the identified label, explained as balloons, aircraft, or natural phenomena. In Socorro's case, no conventional explanation fit. The craft was neither a secret military test vehicle nor an aircraft known at the time. And though some skeptics proposed that Zamora chased a runaway lunar lander from a test program, no such program matched the description of an egg-shaped, four-legged vehicle with a roaring flame. Over the years, further investigations added detail, but not clarity. Interviews with Zamora confirmed his sincerity. He was not prone to exaggeration and did not drink alcohol. Other locals reported seeing glowing lights descending into the same field before Zamora's arrival. The tight timing, Zamora's car chase, the quiet highway, the sudden roar, the witness reactions suggests a single extraordinary event rather than a misidentified ordinary object. The Socorro UFO remains one of the most well-documented close encounters on record. Unlike distant lights in the sky, this was a tangible object, experienced at close range by a trained observer. The Air Force officially closed Project Blue Book in 1969, deeming no UFO posed a threat to national security. Yet for Zamora, the memory stayed vivid throughout his life. He maintained to his death in 2009 that he saw something that night that defied easy explanation. What could the Socorro craft have been? Some argue it was a classified US or Soviet vehicle, tested in secret. But neither side has ever produced records or prototypes matching the eyewitness descriptions. Others suggest hoax or misperception, a reflection of headlights or a chemical flare. But the landing marks and heat-damaged vegetation argue against simple illusions. A few fringe theories propose extraterrestrial origin, citing the craft's unusual shape and the glowing exhaust. While no evidence directly confirms aliens, the incident invites us to ask whether we are alone and whether more advanced visitors might slip through our defenses. Imagine standing in that New Mexico field alongside Officer Zamora. Cool desert air, the scent of creosote bushes, the quiet hum of a distant highway. A sudden flash of light appears, a low roar builds, and a silvery craft rises before your eyes. You feel the heat on your face as it shoots skyward. Then silence returns, broken only by your own heartbeat. In that sharp encounter, the ordinary world fractures for a heartbeat, revealing that reality may hold secrets just beyond our grasp. The D.B. Cooper Skyjacking Mystery. On the afternoon of November 24th, 1971, a man calling himself Dan Cooper bought a one-way ticket from Portland, Oregon to Seattle, Washington on Northwest Orient Airlines Flight 305. Tall, calm, dressed in a dark suit and tie, he carried only a briefcase. Shortly after takeoff, Cooper handed a flight attendant a note. He claimed to have a bomb and demanded $200,000 in unmarked bills plus 4 parachutes. The airline and the FBI quietly arranged his requests, then landed in Seattle to deliver the ransom and parachutes onto the tarmac. Cooper allowed the 36 passengers to leave, keeping the flight crew as hostages. He instructed the pilots to fly toward Mexico City at low altitude, slow speed, and with the rear stairs of the Boeing 727 lowered. A key detail for what came next. Sometime after takeoff from Seattle, somewhere over the heavily forested hills of southwestern Washington, Cooper opened the aft stairs and parachuted into night, carrying the ransom strapped to his body. The plane landed safely an hour later, and Cooper was never seen again. The FBI launched NORJAC, the largest manhunt in agency history at that time, searching rivers, forests, and rural roads. They questioned thousands of suspects, followed hundreds of leads, and examined the suit Cooper left on the plane, still bearing his tie clip and cigarette butts. Yet no definitive trace of the man or the money ever surfaced. In 1980, a boy digging in a sandbar on the Columbia River found a decaying package of several $1,000s and $20 bills, all bearing the exact serial numbers of the ransom, hinting that a fragment of the stash washed downstream. But no other notes turned up, and no remains or gear beside footprint impressions have ever been found. Over the decades, dozens of theories have arisen. One idea suggests Cooper died in the jump, plunging into thick forest or icy water before he could untangle his chute. He carried only a simple civilian parachute, no reserve, and dressed in a suit rather than rugged gear. The low altitude, around 10,000 feet, and darkness of a rainy November night would make a safe landing extremely difficult, especially for someone without specialized training. Yet some argue his calm demeanor and clear instructions imply he had parachuting experience, possibly as a military jumper. Another theory holds that Cooper survived and vanished into the wilderness or a small nearby town. In this scenario, he stashed the money, changed clothes, and melded into the population under a new identity. Over time, he might have spent marked bills cautiously, passed them down to family, or used them in cash-only dealings. The disappearance of nearly all the ransom, apart from the handful of bills found on the sandbar, could mean Cooper broke most of the money into smaller bundles and dispersed it slowly, leaving little detectable trace. A recurring suspect is a man named Robert Rackstraw, a Vietnam veteran and experienced skydiver with a murky record. Investigators found some circumstantial links, similar physical description, parachuting background, and a reported fascination with the case, but no conclusive evidence tied Rackstraw to Cooper. Other suspects include amateur parachutists, career criminals, and even an airline employee who might have known the 727's rear stair mechanisms. In every case, the trail goes cold. Some fringe theories propose Cooper was an intelligence agent using the hijacking to stage a clandestine escape. Others suggest the FBI staged the entire event as a training exercise or to conceal larger operations. These ideas remain speculative, with no documents or whistleblower testimony to confirm them. The D.B. Cooper case holds a special place in American folklore. It is the only unsolved skyjacking in U.S. history. It inspired songs, books, and films, and continues to draw hobbyists who comb forests with metal detectors, form online detective groups, and share new clues. The FBI officially closed its active investigation in 2016, citing exhausted leads and shifting resources to other cases. Yet the agency retains its files as historical archives, open under Freedom of Information requests. Why does the mystery endure? Part of the allure lies in Cooper himself. Polite, professional, almost genteel in his dealings, calling flight attendants ma'am, tipping a spilled drink, neatly folding the ransom checks when passing them through the cabin. He became a symbol of the gentleman outlaw, an everyman who pulled off the perfect crime and slipped into legend. The image of a lone figure disappearing into the night sky, money strapped to his chest, captures the imagination more than a straightforward criminal story. The Taos Hum. In the high desert of northern New Mexico lies the small town of Taos, known for its adobe buildings, clear skies, and art galleries. Yet for some residents, that peaceful landscape carries a persistent, mysterious soundtrack, a low-frequency hum that seems to vibrate in the ears or chest. First reported in the early 1990s, The Taos hum has puzzled locals and scientists alike. Only a few people hear it, maybe 2 or 3 out of every 100, but those who do describe a steady, droning rumble, like a distant diesel engine idling, a distant bass speaker turned up too loud, or even the soft beat of a drum. Investigators have tried hard to locate the source. Infrasound monitors and microphones have scanned homes, streets, and open fields. Geophones, devices that detect tiny ground vibrations, have searched for underground movement. Electrical engineers have checked wiring, transformers, and radio towers. Yet none of these surveys has pinpointed a single culprit. The hum eludes all recording equipment, disappearing when machines are switched off or when investigators leave the area. Some visitors claim they hear nothing, even when longtime Taos residents insist the hum is loud and unbroken. This mismatch between experience and measurement deepens the mystery. One explanation focuses on our bodies rather than the environment. Because the hum sits at very low frequencies, often below 20 hertz, it lies at the edge of human hearing. Some people have more sensitive ears or bodies that pick up these infrasonic waves, feeling rather than hearing them. Studies of infrasound from ocean waves, wind farms, and industrial plants show that even faint vibrations can trigger feelings of pressure, nausea, or anxiety. In these cases, the hum may be real, but too subtle for microphones to capture, yet strong enough for certain listeners to notice. Other theories point to underground sources. Taos sits atop layers of porous rock and ancient river channels. Water flowing through caverns can generate infrasonic waves, similar to the low rumble of a waterfall heard from afar. Tiny shifts in the Earth's crust, microtremors too small to register on national seismic networks, might also create vibrations. Yet detailed geological surveys have not found active water flows or fault movements matching the hum's reported patterns. If such sources do exist, they must be extraordinarily quiet or intermittent. A third idea involves the atmosphere itself. Under special conditions, low-frequency sound from far-off places can bend or duct through layers of air, focusing waves into narrow paths. Sounds from distant power plants, oil rigs, or even ocean storms might channel into Taos on certain nights. In 2014, researchers at the University of New Mexico suggested that microbaroms, steady, low-frequency waves generated by ocean swells, could couple into the ground and re-emerge as audible hum. But if microbaroms are the cause, the hum should affect all residents equally. Yet reports remain highly localized and vary from home to home, suggesting something more personal or site-specific. Psychological factors may add another layer. Stress, fatigue, and anxiety can heighten auditory sensitivity. People suffering from tinnitus, ringing or hissing in the ears, sometimes report hearing external hums that others cannot. In laboratory settings, participants exposed to silence in dark rooms often begin to hear phantom noises. Could the Taos hum arise as a kind of group tinnitus, amplified by expectation and shared stories? That would explain why some newcomers begin hearing the hum after talking with longtime residents. Despite decades of study, no single explanation fits all the facts. The Taos hum remains an auditory ghost, felt by some, denied by many, and impossible to record with our best instruments. It challenges our understanding of what counts as real sound. If only a fraction of people can hear it, does it exist objectively? Or is it a reminder that our senses and minds shape our reality in unexpected ways? The bloop. In the summer of 1997, researchers at the U.S. National Oceanic and Atmospheric Administration, NOAA, listened in on the deep Pacific with a network of underwater microphones designed to track whales and ice movement. One signal startled them, a powerful, ultra-low frequency sound that lasted over a minute and swept across frequencies in a way unlike any known animal, volcano, or earthquake. The noise was so loud it could be detected by sensors more than 5,000 kilometers apart. Scientists nicknamed it the bloop. The bloop's characteristics set it apart. It rose in pitch over about 1 minute, covering a range from roughly 10 hertz, a very low rumble, up to around 50 hertz, still below most human hearing. Its amplitude, its strength, suggested a source at least hundreds of kilometers wide. For comparison, even the loudest whale calls are much weaker and cover different frequency patterns. At first, the bloop sparked wild speculation. If no known animal, geologic event, or human activity made such a sound, could it be a colossal sea creature, larger than any blue whale? Headlines asked whether a monster lurked in the ocean's depths, unseen by all but its own calls. Fictional echoes of Moby Dick and Godzilla danced in the public imagination. Yet marine biologists and geophysicists dug deeper. They pointed out that undersea ice, massive sheets that crack, grind, and rub against each other, can generate powerful, low-frequency sounds. When a giant iceberg calves from an ice shelf, huge chunks of ice fall into the water, creating booms and rumbles. As these ice masses shift and scrape the seafloor in deep channels off Antarctica, they can produce long, loud, sliding noises remarkably similar to the bloop's profile. In 2008, NOAA researchers compared the bloop to recordings of Antarctic ice quakes and calving events. The match was clear. The bloop's frequency sweep, duration, and amplitude aligned closely with known ice-related sounds. These glacial noises can last from a few seconds to several minutes and travel thousands of kilometers through cold, deep water, which acts like a low-loss waveguide for sound. Still, some mystery remains. The bloop's location, off the coast of Antarctica, lies where no human instruments routinely monitor ice movements. The exact iceberg or glacier responsible was never identified. Scientists can model how ice might produce such sounds, but without a direct sighting of a calving event that matches the bloop's timing, a small question mark persists. Beyond the bloop, the ocean holds countless other unexplained noises. There's the Julia sound, a long, constant tone detected in the southern Pacific in 1999, and the slow down noise, a low-frequency sound that slowly decreases in pitch over nearly 2 minutes. Some recordings hint at moving ice, others at undersea earthquakes or volcanic activity. Each sound reminds us that the deep ocean is a vast, dark world filled with phenomena we barely understand. Why do these strange sounds matter? First, they teach marine scientists about ice dynamics and how climate change can alter calving patterns. Second, they help us refine our underwater acoustic networks, which track everything from whale migrations to submarine activity. Finally, they feed our sense of wonder. The idea that enormous phenomena, from moving ice to mysterious creatures, can produce voices that travel unseen beneath the waves. Imagine yourself aboard a research vessel in the Southern Ocean. The night is cold, and a light snow drifts across the deck. You're alone at the hydrophone control panel, watching graphs of sound intensity flicker on the screen. Suddenly, the display leaps as a deep, rising roar fills the speakers. The waveform pulses like a slow heartbeat, climbing in pitch until it fades into silence. You lean back, heart racing, knowing you've just heard one of the ocean's great mysteries. The Pioneer Anomaly. In 1972 and 1973, NASA launched two small spacecraft, Pioneer 10 and Pioneer 11, on a grand tour of our solar system. Their mission was simple: swing past Jupiter and Saturn, send back photos, measure magnetic fields and charged particles, then continue outward beyond Pluto. Engineers expected each probe's power source to last about a decade. Instead, Pioneer 10 kept talking until 2003, and Pioneer 11 until 1995, becoming unexpected long-duration experiments. To track their journeys, controllers on Earth sent a radio ping to each craft and measured the time it took to return. From that delay, they worked out distance. From tiny shifts in the ping's frequency, they deduced speed, down to fractions of a millimeter per second. Beginning in the mid-1980s, analysts noticed the probes were slowing ever so slightly more than expected. That tiny deceleration, about 0.00087, about that too, was far too small to notice on Earth, yet it persisted for years in the cold void. First, engineers searched for mechanical causes. Could tiny leaks in the fuel lines push the probes backward? Or might small thruster firings for course corrections, imperfectly logged, add up to a steady drag? Teams carefully reviewed every line of telemetry, the craft's health reports, and all ground test data. They found no unexplained gas leaks and no thruster firings beyond those planned. The fuel tanks appeared sealed, and every maneuver matched the flight logs. Next came the question of heat. Each Pioneer carried a radioisotope generator, a block of plutonium that decays, producing heat converted into electricity. That waste heat must radiate into space as infrared light. If more heat escaped one direction, the recoil of photons could act like a faint rocket thrust. Imagine the gentle push you feel when standing near a bright spotlight. On the scale of spacecraft, that push matters. From the late 1990s through 2012, several groups built detailed computer models of each probe. They mapped every panel, every instrument, even every cable's surface properties. They simulated how heat flowed through electronics, escaped via louvers, and reflected off the big dish antenna. These thermal models ran scenarios at various distances from the sun and in different orientations, slowly honing in on the pattern of heat emission. By around 2012, most experts agreed that uneven heat radiation, called the thermal recoil force, accounted for the bulk of the mystery. Yet even the best models left a small, unexplained slowdown, a gap between predicted and observed deceleration. Was there still a few watts of heat unaccounted for? Or did this residual hint at something more profound? This lingering discrepancy led some to wonder if our understanding of gravity might need slight tweaking at great distances. Near Earth, Newton's law and Einstein's relativity predict motions with stunning accuracy. But Pioneer 10 and 11 traveled between 20 and 70 astronomical units AU from the Sun, far beyond most tests. Could gravity act a tiny bit differently when accelerations drop below a certain threshold? One proposal, called MOND, modified Newtonian dynamics, adjusts Newton's formula at very low accelerations to explain galaxy rotations without dark matter. If Mond-like effects applied in the solar system's outer reaches, they might show up as tiny drifts in spacecraft paths. Other, more exotic ideas suggested thin halos of dark matter near the Sun, or even entirely new forces that appear only over vast distances. None of these theories has yet matched all observations as cleanly as the thermal recoil solution, but they remind us how little we truly know about the cosmos on its largest scales. The Tunguska event. On the morning of June 30th, 1908, in a remote stretch of Siberian taiga near the Podkamennaya Tunguska River, something immense and mysterious happened. Eyewitnesses up to 60 kilometers away described a bright fireball streaking across the sky, followed by a series of shock waves that flattened trees in a radial pattern. In less than a minute, about 2,000 square kilometers of dense forest were reduced to a carpet of snapped trunks and scorched undergrowth. No impact crater was ever found. This baffling blast became known as the Tunguska event. Early explorers sent by the Russian Academy of Sciences arrived in the region in 1921. They found a circular area of devastation over 30 miles wide, with trees lying flat like fallen matchsticks, all pointing away from a central point. Closer inspection revealed scorched bark and stripped branches on surrounding trees, indicating a blast above the ground rather than a ground impact. Small stones hit by the shockwave were embedded in the soil, but no large meteorite fragments were ever recovered. Scientists quickly realized that nothing human-made could explain the explosion's scale. A conventional bomb could not pack enough energy. An earthquake would leave different damage patterns. Even powerful volcanic eruptions distribute ash and lava, which Tunguska lacked. The leading hypothesis became an airburst, a comet or asteroid tens of meters across, entering Earth's atmosphere at high speed, heating up, and exploding in midair. The tremendous heat and pressure from vaporizing rock and ice produced the shock wave that leveled the forest. Calculations suggest the Tunguska airburst released energy equivalent to 10 to 15 megatons of TNT, hundreds of times more than the bomb dropped on Hiroshima. Yet, without a crater or large fragments, direct proof remained elusive. Comets are mostly ice, which would vaporize completely, leaving little trace. Asteroids are rockier, and fragments might remain, but none fitting the event date have been found. In recent decades, small glassy spheres and microscopic meteoritic particles have been uncovered in soil samples, hinting at extraterrestrial material, but these finds remain sparse. Alternative theories emerged to fill the gaps. Some proposed a fragment of a long-period comet, a body with a loose, dusty structure, exploding in midair. Others imagined a chunk of carbonaceous chondrite, a primitive, carbon-rich asteroid that disintegrated almost entirely. More exotic ideas ranged from natural gas pockets igniting underground to mini black holes passing through Earth, though such notions struggle to match the observed blast pattern and energy. In 2007, and again in 2013, teams surveyed the region using high-resolution satellite imagery and ground-penetrating radar. They confirmed the classic airburst pattern, radial tree fall, an absence of a crater, and evidence of high temperatures. Ice core samples from Greenland ice shear studs revealed tiny spikes in acidity and dust dated to around 1908, consistent with a large explosion in the Northern Hemisphere. Yet, even with modern technology, no smoking gun fragment has emerged. Why does the Tunguska event still captivate us? First, it reminds us that Earth remains vulnerable to cosmic impacts. An object just a few dozen meters wide can devastate a large area if it explodes in our atmosphere. Second, it challenges our ability to detect and track near-Earth objects. In 1908, no telescope network watched the skies. Today, surveys spot many asteroids, but smaller bodies can still slip through unseen. Beyond practical concerns, Tunguska carries a deep human story. Eyewitnesses described windows shaking 70 miles away, nights illuminated like daytime in nearby villages, and cattle stampeded in panic. Local Evenki reindeer herders spoke of thunderous roars and shaking ground. Yet the region's remoteness meant news spread slowly, and political turmoil in Russia delayed serious scientific study for decades. Imagine standing in that Siberian forest at dawn, the sky clear and silent, when a brilliant flash like a second sun rips overhead. You hear a thunderous roar, feel the earth tremble, and then darkness and chaos as trees fall around you. In the aftermath, the forest is transformed into a silent plain of broken trunks, and you wonder how such a force could come from the sky unannounced. Tabby's star. In October 2015, astronomers announced a star, unlike any they had seen before. Officially cataloged as KIC A462852, it soon earned the nickname Tabby's Star after graduate student Tabitha Boyajian, who led the discovery team. Instead of regular, predictable dips in brightness, as planets passing in front of a star would cause, this star blinked in strange, irregular patterns, sometimes dimming by as much as 20% before returning to normal. No known star behaved like Tabby's star. The story began with NASA's Kepler Space Telescope, launched in 2009 to hunt for exoplanets by watching thousands of stars for tiny rhythmic dips in light. Most planet-hosting stars dim by less than 1% as an Earth-sized world crosses their face. But amid the data, Boyajian and her colleagues spotted something odd. KIC 8462852 plunged by up to 22% in 2011 and 2013, then by smaller amounts at other times. The dips lasted days to weeks and showed no clear pattern, sometimes shallow, sometimes deep, sometimes clustered close together, sometimes far apart. The first reaction was skepticism. Could Kepler's instruments be glitching? The team carefully checked for data errors and ruled out obvious defects. Next, they considered the star itself. Young stars often have spots or magnetic activity that makes brightness fluctuate. But KIC 8462852 is a mature F-type star, slightly hotter and more massive than the Sun, showing no signs of youth, no strong X-ray activity, no infrared glow from hot dust as young stars often have. Its light curve anomalies simply did not match any known stellar behavior. That left material between us and the star. A family of comets, or a swarm of dusty debris passing in front of the star, could block light irregularly. If a large cloud of comets, broken apart into fragments, trailed along the same orbit, it might create the uneven dips Kepler saw. Models showed this could work, but it required a phenomenal number of comets, perhaps dozens of giant comets breaking apart all at once, along just the right path. Astronomers found no excess infrared emission to indicate lots of warm dust in orbit, making the comet scenario challenging. The most sensational suggestion came in late 2015. What if an alien civilization had built a massive megastructure around the star? The idea, popularized in science fiction, imagines a Dyson sphere or swarm of energy-collecting panels that would block starlight. If an advanced civilization wanted to capture most of its star's energy, engineers might place giant dark structures in orbit, causing deep, irregular dips as they moved across our line of sight. The notion captured headlines and public imagination, but even proponents acknowledged it was a last resort, a fallback explanation once natural causes failed. To probe the mystery further, astronomers organized observing campaigns with ground-based telescopes and space observatories. In 2016, they measured the star's brightness in different colors of light. If dust were responsible, shorter, bluer wavelengths would scatter more and dim faster than longer, redder ones. Observations showed exactly that pattern, deeper dips in blue light than in red. This color signature strongly suggested dust grains, perhaps from a disrupted body, were blocking the light rather than solid metal panels. Still, the total amount of dust needed remained puzzling, and no infrared glow appeared. Long-term monitoring has added more pieces. Archival photographs from the early 1900s show that Tabby's star may have dimmed by about 20% over the last century, suggesting a gradual trend beyond the sudden dips Kepler recorded. Yet, a later analysis using newer, more precise photometry found no clear century-long dimming. The question remains unsettled due to calibration differences and the star's sparseness in old sky surveys. In 2019, astronomers used the Transiting Exoplanet Survey satellite, TESS, to keep an eye on Tabby's star. TESS's data confirmed the star continues to dip irregularly, though not all dips reach Kepler's depths. Teams are now searching for gas signatures. If a cloud of gas-laden dust passes in front of the star, spectral lines of certain elements might appear or deepen during dips. So far, results are inconclusive, but new observations are planned with powerful instruments like the James Webb Space Telescope. Tabby's star remains a fascinating puzzle. The evidence so far points towards circumstellar dust, perhaps from a family of broken comets or the aftermath of a planetary collision. but the amount and behavior of that dust defy easy explanation. No alien megastructure has been detected, but its possibility reminds us how much we have yet to learn about planetary systems beyond our own. The Voynich manuscript. In an old Italian villa around 1912, rare book dealer Wilfred Voynich uncovered a curious manuscript bound in soft vellum. Its pages were filled with strange, looping script and drawings of plants, astronomical charts, and naked figures bathing in strange tubes of liquid. No one could read its text or identify the plants. Today we call it the Voynich manuscript, after its modern discoverer, and over a century later, its secrets remain locked in its undeciphered pages. The manuscript contains about 240 vellum pages, though scholars believe several are missing. Each page holds lines of unknown writing flowing left to right in neat paragraphs. The illustrations show unfamiliar flowers, roots resembling no known species, star maps arranged in odd patterns, and human figures performing what look like strange rituals or health remedies. The consistently drawn script suggests a single author or workshop, yet the language and alphabet defy every known writing system. Early scholars place the manuscript in the 15th or early 16th century, based on the style of illustrations and carbon dating of its vellum. Some speculated it was a medieval code, perhaps created by monks or alchemists to hide secret recipes for medicine or arcane lore. In the 17th century, it belonged to Rudolph II, Holy Roman Emperor, who paid a fortune for it, believing it was penned by Roger Bacon, the English philosopher and early scientist. That attribution has long been dismissed. Through the centuries, cryptographers and linguists have tried and failed to crack its script. Statistical analyses show its text has patterns similar to real languages. Some words repeat often, others appear only once, and letter combinations follow consistent rules. Yet the alphabet contains characters unseen in Latin or other European systems of the time. No bilingual text has been found to serve as a Rosetta Stone. Even famed codebreakers like William Friedman, who helped break Japan's purple cipher in World War II, devoted years to the Voynich without success. Theories about its content range widely. Some believe it encodes lost herbal knowledge, an illustrated pharmacopoeia of European, Asian, or even mythical plants. Others suggest it's an elaborate hoax, empty writing designed to fool wealthy collectors. But most hoax theories falter because creating convincing, meaningless text with realistic linguistic statistics by hand would take months or years of meticulous effort, with no apparent reward beyond deception. Modern researchers have turned to computers. Machine learning algorithms analyze letter patterns, word frequencies, and image features, comparing them to known languages and botanical databases. Some results hint at similarities with extinct languages of Central Asia or Eastern Europe, but none reach statistical significance. Teams using spectral imaging have examined faint underdrawings in erased text, hoping for clues, yet the underlying message stays hidden. Recent scholarship emphasizes the manuscript's value beyond its undeciphered script. Even without reading it, the drawings teach us about medieval ideas of medicine, astronomy, and natural philosophy. The mix of familiar and fantastic elements, plants that look like lilies but flower underwater, bathing scenes in enclosed pools, suggests The author drew from diverse influences or made deliberate artistic inventions to match the coded text. Today, the Voynich manuscript resides at Yale University's Beinecke Rare Book and Manuscript Library, where scholars worldwide study high-resolution digital scans freely available online. Amateur sleuths, professional linguists, historians, and even artists pore over its curves and illustrations, each hoping to glimpse a pattern others missed. The manuscript has inspired novels, documentaries, and artworks, capturing our collective fascination with puzzles that resist solution. The Hessdalen Lights. In a remote valley in central Norway, near the village of Hessdalen, locals have witnessed strange balls of light hovering in the night sky for decades. First reported in the early 1930s, these Hessdalen lights appear as glowing orbs, white, yellow, or red, ranging from a few meters to several tens of meters across. They dart silently between the hills, linger for seconds to minutes, then vanish without a trace. Despite numerous eyewitness accounts, scientists still debate what causes them. Most sightings occur in a roughly 2-kilometer-long stretch of the Hessdalen Valley, especially near a bend in the road called Light Hill. Observers describe the lights moving horizontally at walking speed, then suddenly shooting straight up at hundreds of kilometers per hour. Sometimes the orbs split into multiple smaller lights or merge into a larger glow. Photographers have captured them on long exposure images, showing streaks of light that trace their unpredictable paths. Beginning in the late 1980s, the University of Tromsø led the Hessdalen Automatic Measurement Station, AMS, a permanent setup of cameras, magnetometers, and radiation detectors to monitor the phenomenon. The AMS records dozens of events each winter, logging light intensity, spectrum, and motion. Spectrometer readings indicate the lights emit a continuous spectrum, peaking in the near-infrared, with temperatures around 2,000–3,000 kelvins, hotter than a candle flame but cooler than an electric arc. Yet the energy source powering these glows remains unclear. Several natural explanations have been proposed. One idea points to rock composition. The valley sits on calcium-rich phosphate and aluminum deposits. When water interacts with these minerals, it can produce tiny charged dust particles that, under certain conditions, ignite in the air. This piezoelectric effect, electricity generated by mechanical stress on crystals, could create luminous plasma balls. Laboratory tests have produced small glowing dust plasmoids, but scaling the effect to meter-wide balls in open air poses challenges. Another theory involves combustion of natural gases. Organic matter, deep underground, can generate methane or radon gas. When these gases seep upward through faults and mix with oxygen near the surface, lightning-like discharges might occur, ionizing the gas and causing it to glow. Radon, a radioactive noble gas, can also emit alpha particles that excite air molecules, potentially producing visible light. However, measurements in Hessdalen have not consistently detected high gas concentrations or radiation spikes during sightings. A third model considers far-infrared light from the Earth's crust. Stress and strain in rocks ahead of geological faults can release electromagnetic waves, which travel through the ground and emerge in valleys. If the valley acts as a natural waveguide. These waves could concentrate energy into luminous standing plasma. Yet correlating light events with a measurable seismic or electromagnetic precursor has proven difficult. Skeptics suggest some sightings may be misidentified aircraft lights, distant car headlights, or ordinary sources seen through fog or mist. But the most compelling reports come from clear nights, with multiple witnesses watching lights move against the star field, impossible to explain as fixed or distant objects. In a few cases, military aircraft activity in the region has coincided with lights, but the shapes, colors, and behaviors differ from known flares or drones. International teams continue to study Hessdalen. In 2018, a European research expedition brought mobile sensors, drone-mounted cameras, and high-speed spectrometers to capture more detailed data. Early results confirm variability in the light's chemical emissions, sometimes showing sodium and calcium spectral lines, other times none, pointing to heterogeneous sources or processes. The Hessdalen lights remind us that even on our own planet, there remain phenomena that defy simple classification. They blend geology, atmospheric science, and plasma physics into a puzzle that has endured for nearly a century. For the locals, the lights are part of daily life. Tourists come and go, while villagers speak of their silent dances with familiarity and wonder. Imagine yourself standing on a snow-dusted road under an Arctic sky. The air is still, each breath visible in the beam of your flashlight. Suddenly, ahead in the valley, a pale yellow orb appears, hovering above a pine stand. It drifts toward you, pauses as if curious, then darts upward and vanishes behind a ridge. You wait, heart pounding, as silence returns, only the whisper of wind through the trees. In that fugitive glow lies a question the night keeps for itself. Oumuamua, the mysterious interstellar visitor. In October 2017, astronomers scanning the night sky with the Pan-STARRS telescope in Hawaii spotted an object unlike anything they had seen before. It moved so quickly and on such a steep path through the solar system that they realized it must have come from outside our own stellar neighborhood. The first known interstellar visitor was soon named One Aise Oumuamua, Hawaiian for scout or messenger. Its brief flyby left more questions than answers, and to this day, Oumuamua remains one of the most intriguing puzzles in modern astronomy. At first glance, Oumuamua looked like a small, sun-bleached rock, perhaps a few hundred meters long. Its brightness changed dramatically as it tumbled through space, suggesting a cigar-like shape roughly 10 times longer than it was wide. Most asteroids and comets we know are more rounded or irregular, but Oumuamua's extreme elongation seemed unprecedented. In addition, it showed no visible signs of a cometary coma, no gas or dust cloud glowing around it, even as it passed closest to the Sun at 0.25 astronomical units, where ices usually vaporize. Then came the second surprise. Precise measurements of Oumuamua's trajectory revealed a tiny, extra push away from the Sun, an acceleration too large to be explained by gravity alone. Comets often show similar behavior when solar heat sublimates ice into gas, producing outgassing jets that act like natural rockets. Yet astronomers looked hard and saw no signature of gases, no spectral lines of water, carbon monoxide, or other volatiles, no dusty tail drifting behind. The question arose, what could be fueling that extra burst of speed? Several explanations have been proposed. One idea resurrects the comet hypothesis, but with a twist. Oumuamua could be covered in a thick crust of dark organic material that masks any sublimating ice below. As sunlight warmed its surface, hidden pockets of ice might have released faint jets too weak or sporadic to detect, yet enough to nudge its path. This model fits some data, but requires an unusually insulating crust and a precise distribution of ice beneath. Another theory suggests radiation pressure, the gentle push of sunlight itself, might account for the acceleration if Oumuamua were extremely thin, like a light sail, perhaps only a millimeter thick. Solar photons carry momentum, and on a flat, reflective surface, they can impart measurable force. If Oumuamua were a natural fragment of carbon-rich material, flattened by unknown processes in its home system, sunlight alone could push it slightly off course. This idea thrilled science fiction fans, but raised questions. What natural mechanism could produce such a thin, broad sheet of material hundreds of meters long? More exotic explanations have even ventured into the realm of the artificial. A small team at Harvard suggested Oumuamua might be a derelict probe or sail sent by an advanced civilization, its unusual shape and unexplained acceleration reflecting technology rather than nature. While no direct evidence supports this claim, it underscores how irregular and unexpected Oumuamua's behavior was, and how reluctant some are to dismiss any possibility. Sadly, Oumuamua's brief visit left little time for follow-up. It was discovered after perihelion, its closest approach to the Sun, and within weeks it receded toward the outer solar system, growing too faint for detailed observation. Telescopes around the world trained every available instrument on it, but even the most powerful could only capture a handful of spectra and high-precision positional data. By January 2018, Oumuamua had faded beyond reach, leaving behind only the data collected in its fleeting appearance. Since then, astronomers have searched for similar interstellar objects. In late 2019, comet 2I Borisov entered our solar system, showing unmistakable cometary activity, a curved tail of gas and dust, and confirming that interstellar visitors come in different flavors. Borisov behaved like a conventional comet from another star, but Oumuamua remains unique in its odd acceleration, extreme shape, and lack of visible outgassing. Oumuamua's legacy goes beyond its own mysteries. Its discovery proved that surveys were sensitive enough to catch interstellar interlopers, and that such objects may be common, wandering invisibly through the galaxy until chance brings them near a star. Future telescopes, like the Vera C. Rubin Observatory, promise to find dozens of these visitors each year, giving us chances to study their properties in detail and compare their behaviors. Imagine standing under a dark sky, your telescope trained on a faint point of light speeding past the sun's glare. That small scout, born in a distant stellar nursery, perhaps millions of years ago, settles your gaze on the vastness of interstellar space. Fast radio bursts. In 2007, Radio astronomers analyzing archival data from Australia's Parkes Observatory stumbled upon a surprise: a single millisecond-long flash of radio waves so bright that it must have originated from billions of light-years away. They called it a fast radio burst, or FRB. Since then, dozens more have been detected by telescopes around the world, brief, powerful pulses that outshine whole galaxies at radio frequencies before vanishing faster than the blink of an eye. For nearly 2 decades, their cause has remained one of astronomy's hottest mysteries. FRBs arrive unpredictably from random directions in the sky. A typical burst lasts less than 1,000th of a second, but carries as much energy in radio waves as the sun emits in a day. The first FRBs were found in old data, but once researchers knew what to look for, real-time surveys began to catch them live. In 2015, astronomers using the Green Bank telescope in West Virginia spotted a burst and immediately alerted observatories worldwide. An astronomer might scramble from a dinner party to aim a telescope at the right spot within minutes. One of the biggest puzzles was whether FRBs repeat. If each burst came from a cataclysmic event, like a star exploding or two black holes merging, it should happen only once. Yet in 2016, a team led by the Canadian Hydrogen Intensity Mapping Experiment, CHIME, found an FRB that flashed 6 times over 10 minutes. Since then, several repeating FRBs have been cataloged, some with hundreds of bursts over days or months. The repeating behavior allows astronomers to study their sources more closely, narrowing down possible explanations. What kinds of cosmic engines can produce such brief but intense flashes? The leading candidates are neutron stars, city-sized objects formed when massive stars collapse in supernova explosions. Neutron stars can spin hundreds of times per second and have magnetic fields trillions of times stronger than Earth's. If 2 neutron stars collide, they can produce a single burst. If an isolated neutron star experiences sudden changes in its magnetic field, a starquake, it might emit repeating bursts. One popular model involves magneteers, a rare type of neutron star with extremely strong magnetic fields. In April 2020, astronomers detected an FRB from within our own galaxy, the Milky Way, that matched a flare from a known magnetar called SGR 1935 plus 21554. The radio burst was far weaker than extragalactic FRBs, but provided the first direct link between magnetar activity and fast radio flashes. This discovery lends weight to the idea that distant FRBs may also come from magnetars, though they must be far more energetic or seen under special conditions. Still, not all FRBs fit the magnetar pattern. Some repeat in complex ways, with quiet periods lasting months and then rapid-fire bursts for days. Others show subtle changes in their radio frequencies or arrival times that hint at their signals passing through intervening gas and magnetic fields. By measuring these dispersion effects and frequency drifts, astronomers can use FRBs as probes of the intergalactic medium, mapping the distribution of matter between galaxies. Another intriguing idea is that FRBs arise near supermassive black holes at galaxy centers. The extreme gravity and magnetic fields there could twist and snap magnetic field lines, producing pulses of radio energy. Or perhaps FRBs come from collisions between neutron stars and black holes, or from exotic objects like cosmic strings, hypothetical cracks in space-time. Each scenario has its own signature in burst duration, energy, and repetition pattern. To catch more FRBs and study their hosts, astronomers are building new instruments. CHIME in Canada has revolutionized the field by detecting dozens of FRBs each month. The Australian Square Kilometre Array Pathfinder, ASCAP, can pinpoint bursts to specific galaxies. Soon, the Deep Synoptic Array and upgrades to the Very Large Array will provide even more precise localizations, telling us exactly which galaxy an FRB sprang from, and allowing follow-up observations in visible light and X-rays. Fast radio bursts remind us that the universe still hides powerful, fleeting events that challenge our understanding of extreme physics. They blend stellar remnants, magnetic monsters, and cosmic magnetic fields into a puzzle that unfolds in milliseconds. Each new detection sharpens our picture, but the full story, how many types of FRBs exist, and what exactly powers each burst, remains unwritten. The Marfa Lights. On clear nights near the small town of Marfa, Texas, drivers along U.S. Highway 90 sometimes spot flickering orbs of light dancing just above the desert floor. Known as the Marfa Lights, these glowing balls, white, yellow, orange, even red or green, appear singly or in groups. They bob up and down, split apart, merge together, and sometimes zip off at speed. For over a century, people have watched them in wonder, yet no one has agreed on a single explanation. Reports date back to the 1880s, when cowhands drove cattle across the wide, empty plains. They spoke of ghostly campfires lighting the horizon at night, only to vanish when riders drew closer. In the 1950s, local newspaper editor Robert Reed organized informal watch parties. He even built a viewing platform, now called the Marfa Lights Viewing Area, where visitors still gather after dusk. Despite thousands of onlookers and even television crews, the lights remain unpredictable. Some nights dozens appear, other nights none at all. One simple idea points to car headlights. Traffic on the distant US 67 or ranch roads could reflect off low-lying clouds or atmospheric layers, creating faint but moving glows. Light bending, or refraction, through layers of warm and cool air can bend beams over the horizon. A car's headlights, refracted just right, might seem to hover and dance. Experiments confirm that under certain temperature conditions, headlight beams can bend and appear floating. Yet skeptics note that the lights have been seen on nights with no traffic, and at angles that don't match known roads. Another theory blames natural gas. The old Marathon oil field lies nearby, and decaying organic matter underground can release methane. When methane mixes with oxygen, it can ignite above the ground in small, flickering flames, fiery orbs that bob and drift. These will-o'-the-wisp fires are well known in damp marshes, where swamp gases burn at the water's surface. But Marfa's dry desert has little surface water, making spontaneous gas ignition less likely. Surveys have found only trace gas leaks in the area, not enough to account for bright, moving lights. Electromagnetic effects offer a different possibility. The remote desert experiences strong temperature swings between day and night. These changes can stress rocks, generating electric charges in quartz and other minerals, a phenomenon called the piezoelectric effect. If enough charge builds up, it could create small electrical discharges in the air. Those discharges might glow as faint plasma balls. Laboratory tests show that stressed quartz can produce flashes of light, but scaling such tests to natural conditions, producing visible orbs meters across, remains unproven. Psychological and visual factors also play a role. In a dark, empty landscape, our eyes can play tricks. A distant light seen against a featureless sky can seem to move as you shift your gaze due to a small tremor in our eye muscles called a microsaccade. If you focus on a point near the light appears to drift. Many visitors track the lights without a clear frame of reference, making false motion seem real. At the same time, the desert's isolation and reputation set up an expectation. If you believe you might see ghost lights, you're more likely to interpret any faint glow as something mysterious. Scientists have tried to capture the Marfa lights with instruments. Weather balloons, infrared cameras, magnetometers, and all-sky cameras have monitored the viewing area on dozens of nights. Many captures show no lights at all. On nights when lights do appear, footage sometimes correlates with distant vehicle headlights or ranch lights. But on other nights, no vehicles or known sources match the orb's behavior. Researchers from Texas State University concluded that while some Marfa lights come from cars, others remain unexplained. In recent years, enthusiasts have added drones and automated light sensors to the hunt, hoping to rule out man-made sources once and for all. High-resolution time-lapse photography reveals that some orbs flicker in intensity and color more rapidly than any car's headlight could. Others split cleanly into 2 or 3 lights, moving in ways unlike known artificial sources. The Marfa lights endure as a blend of natural science and folklore. To some, they are reminders of the land's history, ghost fires of long-gone settlements, or reflections of cattlemen's lanterns. To others, they are purely physical phenomena, waiting for the right mix of atmosphere, geology, and light to ignite. For tourists, they are a night's mystery, a chance to peer into the unknown. The Devil's Kettle Waterfall. On the north shore of Minnesota's Lake Superior, the Brule River splits around an island just before plunging 30 feet over 2 adjacent falls. One side flows normally into Devil's Kettle Falls, but the other side drops into a deep, smooth-walled hole, an ominous kettle, and vanishes from sight. Where does that water go? For years, the Devil's Kettle baffled visitors and scientists alike. Early explorers and tourists tossed objects, stones, sticks, even tennis balls, into the kettling hole, hoping to hear a splash or spot them downstream. None ever turned up. The hole's sheer rock walls echo only a muffled roar, and probes sent down get tangled in unknown crevices. Local lore speaks of underground rivers or secret springs feeding distant lakes. Some whispered of hidden caves leading far beneath the earth. The hole looked like a mouth swallowing half the river's flow, leading nowhere visible. In the 1990s, Minnesota's Department of Natural Resources, DNR, set up dye tests. They poured harmless fluorescent dye both into the kettle and into the main channel upstream, then watched for colored glow downstream where the Brule feeds Lake Superior. The normal side showed dye within minutes, but the kettle's dye never appeared, at least not where they looked. Efforts to trace the water by monitoring downstream beaches and river mouths yielded no clear sign of the missing volume. Scientists next tried measuring the river's flow rates on either side of the split. They used flow meters and timed floats, carefully accounting for seasonal changes. Remarkably, the combined flow below both falls consistently matched the total flow above. In other words, the lost water from the kettle seemed to rejoin the main channel somewhere below the falls, but not in a spot obvious to observers. Geologists examined the rock around Devil's Kettle. The falls cut through layers of basalt and volcanic ash, solid and unfractured, except for the kettle itself. The hole appears to be an old pothole formed by swirling pebbles in a shallow pool long ago, gradually enlarging into today's chasm. There's no sign of large cracks or tunnels leading away. Any underground passage big enough to swallow half the river would likely need sizable caverns, which do not show up in ground-penetrating radar or seismic surveys. In 2016, a detailed DNR study brought in hydrologists, cave experts, and sonar equipment. They floated ping-pong-sized sonar buoys into the kettle and tracked echoes, hoping to map an underground channel. The sonar suggested a steep rock ledge at the kettle's bottom, then an abrupt drop into darkness, too deep for their instruments. Yet when they compared flow measurements above and below, they again found virtually no difference, implying that the water emerges somewhere back into the visible river course. One simple explanation is that the kettle spillway drops water into a hidden pocket that immediately spills back into the main river downstream, beneath a submerged rock ledge. The turbulence of the falls could trap floats and die in small eddies where they decay or sink, making them hard to detect. Heavy debris, sand, and small stones could fill and block lower passages, forcing water to seep through cracks rather than flowing swiftly enough to carry floats or die. Another idea points to absorption into fractured rock. Even hard basalt can develop tiny cracks over millennia. The kettle's swirling waters may slowly erode these fractures, opening micro-pathways where water seeps before reappearing below. Dye molecules, which bind to sediments or cling to algae, might get captured and held in porous rock, never making the return journey to the main flow in detectable amounts. Environmental factors complicate tracing. Cold temperatures suppress algae growth, reducing dye visibility in winter. High spring flows can flood instruments, while summer's low flows make side channels more active, shifting where water resurfaces. Dye tests that failed to spot colored water downstream might have simply missed the right reentry point, or dye concentrations fell below detection thresholds. Despite modern equipment and repeated studies, the Devil's Kettle keeps its secret. The bulk of its water cycles back into the river unseen, while objects and test tracers vanish into the abyss or cling to hidden cracks. The mystery reminds us how dynamic even small river systems can be, carving their way through solid rock into configurations that defy easy observation. Spontaneous human combustion. Imagine a quiet sitting room late at night. A lone figure slumps in a chair, reading, or watching television. In the morning, firefighters arrive to find the skeleton of that person in what once was their living room, charred to ash, while nearby furniture, curtains, and even the carpet remain surprisingly intact. No source of ignition, no accelerants, no evidence of a fire spreading beyond the body. This unsettling scenario has been reported dozens of times over the past 300 years under the name spontaneous human combustion, SHC. The first recorded case dates to 1745 in Ireland, when Countess Cornelia van der Klenke's body was found reduced to ash, her head and feet unharmed. Since then, more than 200 cases have been catalogued worldwide, often involving elderly or infirm individuals who lived alone. Witnesses sometimes describe a faint, sweet odor in the room, or a small flame flickering before the blaze consumes the victim. But in every case, the fire seems to begin within the body itself, without any external spark. Skeptics argue that SHC is simply a misinterpretation of ordinary fires. A dropped cigarette, a knocked-over lantern, or faulty wiring could ignite the victim's clothing. Once the body catches fire, fat acts like a slow, burning candle fuel, sustaining heat at the torso long enough to consume flesh. This wick effect occurs when melted human fat soaks into clothing, feeding a low-temperature, smoldering fire. Autopsies of SHC victims often show their bodies burned heavily in the torso, while extremities remain intact, exactly what the wick effect predicts. Laboratory tests support this idea. In one experiment, animal fat wrapped in cloth could smolder for hours at temperatures above 1000 DGF, turning bones brittle and ash-like. Nearby objects, insulated by air pockets or hardwood floors, stayed unscathed. Likewise, bodies contain large fat deposits around the chest and abdomen, and clothing layers can trap heat. Under the right conditions, a small ignition source, perhaps a spark from a pipe or a smoldering cigarette, could start the process without witnesses noticing. Yet not all SHC cases fit neatly into the wick effect model. In some reports, the victim's body is almost entirely consumed, far beyond what lab tests predict, while nearby objects show no sign of heat exposure. Floors, walls, and furniture stand intact, and soot is minimal. In rare instances, tiny droplets of fatty material have been found sprayed on mirrors and walls, as if the body's contents exploded outward. These odd details fuel the idea that SHC might involve factors beyond a simple smoldering fire. Various alternative theories have been proposed. One attributes SHC to static electricity buildup, common in dry winters in old houses, causing a discharge inside the body's tissues. Another points to high levels of acetone in the victim's bloodstream, perhaps from conditions like diabetes or alcoholism, which could make tissues more flammable. Some have suggested exposure to environmental chemicals or radiation that might ignite fatty acids within cells. However, no conclusive evidence ties these factors to actual SHC incidents. Psychological and social factors also play a role. Many SHC victims are elderly, isolated, and perhaps in poor health, making them less able to respond to a small fire. An unattended cigarette could smolder unnoticed for hours. The strange details, dripping fat, partial destruction, capture public imagination, leading newspapers and later television programs to sensationalize the cases. Over time, SHC has gained a macabre allure, with each new report adding to its mythos. Modern forensic science generally views SHC as a subset of house fires, where the wick effect is the dominant mechanism. Fire investigators look for external ignition sources first, then consider victim-specific factors: health, medications, posture, clothing. In cases where no clear spark is found, the wick effect offers a plausible explanation without invoking mysterious internal combustion. Despite this, SHC remains a haunting concept. The idea that our own bodies might turn against us in a secret, fiery process. It shows how real events, unusual burn patterns, unexpected victim profiles can inspire legends when viewed without context. As you listen tonight, imagine the gentle crackle of a hearth fire, then the faint glow of embers hiding a secret flame. Let the story remind you of both our vulnerability and the power of critical inquiry. And as your thoughts settle, may you find warmth in knowledge rather than fear. The Sailing Stones of Death Valley. In the vast, dry basin of California's Death Valley National Park lies a flat, mirror-smooth area known as Racetrack Playa. Visitors marvel at its silent emptiness, broken only by a curious sight: stones of various sizes scattered across the surface, each with a long, straight track carved in the clay. These sailing stones seem to move on their own, leaving trails behind them, even though no human, animal, or engine could have dragged them. For decades, this phenomenon puzzled scientists and park rangers alike. The tracks stretch from a few inches to hundreds of feet, sometimes straight, sometimes curving gently, but always etched into the soft mud. Stones range from pebbles to rocks, weighing tens of kilograms. Their paths cross each other, diverge, or converge with no obvious pattern. In early photographs from the 1940s and 50s, rangers noted fresh tracks but never saw the stones move. Explorers speculated on wind, animals, or underground currents, but none fit the facts. Wind alone cannot push a heavy rock across slippery mud, at least not without tipping it over or leaving chaotic slide marks. And there are no hoof prints or tire tracks to suggest animal or vehicle involvement. Geothermal heat from beneath the ground warms the clay, but no steam vents or hot springs exist on the playa's surface. Water is scarce most of the year. When it appears, it forms only a thin, shallow pool that evaporates in days under the baking sun. In the 1970s and 80s, geologists Jason and Patricia Sharp first mapped the stones and documented their trails. They measured rock weights, track lengths, wind speeds, and clay conditions, but still found no clear mechanism. The stones moved only when conditions were just right. The clay had to be wet enough to soften, but not so wet that the stones sank. Wind speeds had to be strong yet steady, and the sun had to bake the surface to a leathery crust. Even then, the energy required to push a 20-kilogram rock would exceed any reasonable gust. The mystery deepened until the 2010s, when researchers set up an ambitious experiment. They tagged dozens of stones with small GPS devices and time-lapse cameras, then waited for the right season. In early 2014, after a winter storm dumped rain into the basin, thin water covered the playa. Overnight, temperatures plummeted below freezing, forming a delicate layer of ice a few millimeters thick. When the morning sun warmed the ice, it cracked into large, floating panels only a few centimeters thick. As the ice sheets melted, a gentle breeze, only about 5 to 10 miles per hour, pushed the floating panels across the shallow water. The panels, in turn, nudged the stones, causing them to slide slowly along the wet clay. Because the ice was thin and flexible, it moved in broad sweeps, carrying stones in straight lines. When panels broke or melted, stones paused. Over a few hours, tracks dozens of meters long appeared in directions matching wind patterns recorded that morning. The GPS units confirmed the stones' movements. Some shifted only a few centimeters, others slid up to 80 meters in a single event. High-resolution video showed ice fragments pushing and pivoting the rocks, sometimes from their sides, sometimes lifting and dropping them to create sharp turns. The effect was subtle and slow. No sudden jumps or tumbles, explaining why no one ever saw the stones in motion without specialized equipment. These observations solve the long-standing riddle. It takes a rare combination of rain, freezing nights, and light winds to set the sailing stones adrift. In most years, one or more of these conditions fails, so stones stay put and tracks fade under sun and wind. That's why the phenomenon seems so mysterious and why tracks appeared irregularly. Beyond solving a natural curiosity, the sailing stones teach us broader lessons about the interplay of water, ice, wind, and land. They remind us that even in the driest deserts, water can briefly transform landscapes, that thin sheets of ice can move heavy objects when conditions align, and that patient observation over decades with the right tools can reveal nature's hidden mechanics. Imagine yourself standing on the hard-baked mud of Racetrack Playa at dawn. A thin mist lifts from the surface, and you feel a chill in the air. You watch as slender ice panels glide silently across shallow water, nudging a dark stone along a newly forming track. The stone slides slowly, leaving a crisp line behind it. As the sun rises, the ice melts, and the tracks harden in the clay, a record of nature's quiet dance. The Mpemba effect. Imagine two glasses of water on a kitchen counter, one filled with hot water from the kettle, the other with cool tap water. You place both in a freezer and come back later to find, surprisingly, that the hot water has frozen solid before the cooler one. This counterintuitive observation is known as the Mpemba effect, and despite decades of experiments, scientists still don't agree on exactly why it happens. The story begins in 1963 in Tanzania, when a high school student named Erasto Mpemba discovered the effect by accident. He was making ice cream in class, stirring milk and sugar mixture in a pan over heat, then chilling it. One day, he put the still warm mixture into the freezer alongside cups of cool water, intending to cool it down before mixing. To his surprise, his warm mixture froze before the cooler samples. His teacher dismissed the claim, but Mpemba mentioned it at university years later. where a visiting physicist, Dr. Dennis Osborne, heard the story. Together, they published a paper in 1969 describing hot water freezing faster than cold under certain conditions. Since then, researchers around the world have tested the Mpemba effect with water and other liquids. Some see it reliably, others never do. It seems to depend on details like the shape of the container, how much water you use, the freezer's properties, and even the water's purity. That variability makes designing controlled experiments tricky and comparing results challenging. Several explanations have been proposed, often working together rather than as a single cause. 1. Evaporation. Hot water loses more mass to evaporation before freezing begins. Less water means it takes less time to reach the freezing point. If the hot sample loses 5 to 10% of its mass, that reduction can speed up freezing significantly. However, evaporation alone doesn't explain all observations, especially in closed containers where evaporation is limited. 2. Convection currents. Warm water sets up stronger convection, circulating currents that mix the water more thoroughly. This mixing moves the warmer water at the bottom to the surface, dissipating heat faster overall. In cooler water, stratification, layers of different temperature, can slow cooling, while in hot water, vigorous stirring by convection speeds uniform cooling. 3. Dissolved gases. Heating water expels dissolved gases like oxygen and carbon dioxide. Some scientists suggest that gas-rich water freezes more slowly, perhaps because bubbles interfere with ice crystal formation. When hot water loses those gases, it may freeze faster. But experiments have found mixed results on how much dissolved gases affect freezing rates. 4. Supercooling. Pure, undisturbed water can cool below its normal freezing point, 0 degrees, without forming ice crystals. This is called supercooling. Ice formation then happens suddenly and rapidly. If cooler water supercools more than hot water, it spends more time below 0 degrees before crystallizing. Meanwhile, hot water might cool to exactly 0 degrees Celsius and freeze without supercooling delays. Supercooling is highly sensitive to impurities and container surfaces, making it tricky to predict. 5. Frost and surface effects. Placing a hot container in a freezer can melt frost on the freezer shelf, creating a thin layer of water that refreezes. This additional ice layer improves thermal contact between the container and shelf, speeding heat transfer. In contrast, a cold container placed on old frost makes poorer contact, slowing its cooling. This subtle effect varies with freezer design and frost buildup. Most researchers now believe the Mpemba effect arises from a combination of these factors, their relative importance changing with each experimental setup. No single theory covers every case. The effect highlights how a seemingly simple process, water freezing, can involve many interacting variables and physical processes we don't fully control. Beyond its scientific puzzle, the Mpemba effect reminds us of the value of observation and curiosity. Mpemba's original discovery came from noticing something unexpected in a school kitchen, questioning it, and following up, even when adults dismissed his observation. That spirit, paying attention to the everyday world and testing what seems obvious, drives scientific progress. The Mpemba effect also has practical implications. In industrial processes that rely on rapid cooling, such as freezing food or certain chemical reactions, understanding how to optimize conditions could save energy and time. Engineers design cooling systems with precise control over fluid mixing, container design, and thermal contact, all factors linked to the Mpemba puzzle. The Bermuda Triangle, off the southeastern coast of the United States, bounded roughly by Miami, Bermuda, and San Juan, lies a patch of ocean known for strange tales of ships and planes disappearing without a trace. Dubbed the Bermuda Triangle, this region has inspired legends for over 7 decades. Vessels vanish, radio communications cut out, and wreckage remains elusive. Tonight, let's drift into the warm Atlantic breezes and explore how ordinary forces can intertwine with misperception to create lasting mystery. The modern legend began in December 1945, when 5 Navy torpedo bombers called Flight 19 took off from Fort Lauderdale for a routine training mission. Radio contact went quiet as the flight leader reported his compass malfunctioning and ocean currents disorienting the group. All 5 planes, plus a PBY search and rescue flying boat sent to find them, disappeared. No bodies were ever recovered. Soon the press seized on the story, weaving notions of alien abductions, magnetic anomalies, and undersea civilizations into the triangle's lore. In the years that followed, writers compiled other incidents into a growing dossier. A British South American Airways flight vanishing in 1948. Cargo ships, like the Carroll A. Deering, found deserted in 1921. The yacht Seabird disappearing in 1750. Some vessels reappeared mysteriously, sails trimmed, logs untouched, while others left no sign of struggle or distress. As word spread, the Bermuda Triangle became shorthand for marine and aeronautical enigma. Yet a closer look reveals that many supposed mysteries have clear, natural explanations. The Atlantic's weather can shift rapidly. Sudden storms with towering waves can overwhelm ships and toss small planes into turbulence. The triangle falls within the Gulf Stream, a powerful ocean current that can carry debris far from wreck sites, hiding evidence. Underwater, the continental shelf drops off steeply, and deep-sea currents can scatter wreckage, making recovery difficult. Instrument error also plays a role. The Earth's magnetic field does tilt slightly in the triangle area, but not enough to disrupt modern compasses significantly. Early aviators relied on less precise navigation tools, and in poor visibility could become disoriented. Flight 19's lead pilot did report compass trouble, but audio transcripts show he also misread his charts and misunderstood wind conditions. Miscommunication between pilots and controllers compounded the confusion, turning a navigational error into a legend. Human psychology amplifies the oddness. When a well-skilled pilot vanishes, we expect glaring evidence: a crashed fuselage, lifeboats aflame, frantic messages. But if a crew overlooks a navigational miscalculation, they may glide into low fuel, descend into storm clouds, or crash in remote waters, leaving little to find. Then a small number of dramatic losses stands out amid thousands of safe crossings, creating a skewed sense of danger. Researchers at the U.S. Coast Guard and insurance companies have studied the triangle's incident rate and found it no higher than in similarly busy shipping lanes or flight corridors. Thousands of vessels pass through every year without trouble. Modern tracking systems, GPS, radar, and satellite communications now alert authorities if a plane deviates or a ship goes off course. Since these technologies became widespread in the 1970s and 80s, unexplained vanishings in the area have dropped sharply. That doesn't entirely erase the triangle's allure. The ocean still hides up to 95% of its seabed, and catastrophic failures at sea or in flight can yield wrecks too deep or scattered for practical recovery. Telltale debris fields can become buried in sediment or sucked into underwater canyons. Radio blackouts can last long enough to seed rumors. Why did their final message cut off mid-sentence? Such gaps invite speculation, loose ends that fans of mystery delight in tying into grander theories. Popular culture has kept the legend alive. Books in the 1970s, followed by television specials and dramatic films, painted the triangle as a gateway to the unknown, a place where science meets science fiction. Even today, cruise ships offer Bermuda Triangle tours, highlighting alleged hotspots with concession stand dramatics. Yet for each tale of eerie disappearances, countless captains report nothing unusual beyond routine storms and navigational checks. Imagine yourself on the deck of a small cruiser, sea breeze warm, the sun setting in pink and gold. A line of cloud builds on the horizon, fast moving, low to the water. Your compass aligns steadily with GPS on your phone. You ease into the Gulf Stream's current and feel the gentle tug at the hull. Even here, where legend looms, the ocean moves by predictable laws: wind, waves, and tides. If storms break or equipment fails, rescue radios and beacons now guide help your way. The Red Rain of Kerala. In the summer of 2001, residents of Kerala, a state on India's southwest coast, awoke to an astonishing sight. Rainwater dyed bright red. Over the next 2 months, more than 100 such colored downpours fell, staining clothes, rooftops, and streets in hues ranging from pink to deep crimson. Locals called it blood rain, and scientists rushed in to find out what turned the clouds into crimson. Initial tests on the red water showed tiny particles, microscopic red cells, suspended in the droplets. Some researchers thought these were spores from algae or fungi, blown inland from nearby forests or carried aloft by winds. Spores are common in the atmosphere, and during rainy seasons, heavy winds can lift them high enough to fall back down with precipitation. If enough spores concentrate in a cloud, the rain can take on vivid colors. To investigate, teams collected samples directly from fresh downpours and examined them under microscopes. The cells were round, about 10 micrometers across, and lacked obvious internal structures like nuclei. Chemical analyses showed they consisted mainly of carbon and oxygen, similar to organic material. Yet they resisted identification as any known species of algae, fungus, or pollen. No DNA could be reliably extracted, leading some to wonder if the cells were living organisms at all. A few scientists proposed a more exotic origin: meteoric dust, or fragments of a disintegrating comet. In late July 2001, Sriharikota, India's satellite launch center, had sent up its first GSLV rocket. Some speculated that exhaust or upper stage debris had seeded the upper atmosphere with microscopic particles. When rain condensed around these particles, the droplets took on color. However, the timing and locations of the red rains did not align neatly with rocket trajectories, and similar rains occurred before and after launches. The lack of genetic evidence deepened the mystery. If the red cells were terrestrial spores, they should yield DNA sequences matching known organisms. Yet, repeated attempts to amplify DNA produced only faint or inconsistent signals. Some researchers suggested the cells might be dead or preserved in a way that blocks DNA extraction. Others argued that the extraction methods were unsuitable for unusually tough cell walls, and that more advanced techniques might reveal familiar genomes. In 2006, a group led by scientist Godfrey Lewis at Mahatma Gandhi University revived interest with a startling claim. The red cells showed survival traits unlike ordinary life. They reported that the cells could withstand temperatures up to 300 degrees C, grow in extreme pH solutions, and even resist powerful chemical solvents. Such resilience hinted at an origin beyond Earth, perhaps microbial life delivered by an incoming meteor or comet fragment, a form of panspermia. But these extraordinary results drew skepticism from microbiologists who questioned the experimental controls and reproducibility. Subsequent studies leaned back toward a terrestrial explanation. Researchers collected air samples from dry seasons and found dust-laden spores similar in appearance to the red cells. Advanced DNA sequencing finally picked up traces of bacterial and fungal genes in some samples, linking the cells to known organisms, albeit in unusual forms or concentrations. Atmospheric models showed that monsoon winds from Africa could carry desert dust and biological debris across the Arabian Sea to Kerala, depositing vast quantities of particles in city clouds. Still, questions remain. Why did the cells appear only during certain months? Why did some rains run clear, even in the same storms? And why were the cells so abundant, millions per milliliter of rain, at levels far higher than typical airborne spores? Some suggest local factors: dust from nearby dry riverbeds stirred by seasonal winds, combined with monsoon dynamics to concentrate spores in rain-bearing clouds. Others note that Kerala's unique topography, with hills rising rapidly from the coast, could force low clouds upward, causing sudden cooling and heavy, localized showers that sweep dense spores out of the air. Beyond the scientific debates, the red rains left an impression on Kerala's culture. Local newspapers printed photos of crimson puddles and stained umbrellas. Folklore wove the phenomenon into legends of divine omens. Tourists arrived hoping to glimpse the colored downpours, sparking a brief red rain tourism boom. Even in years without red rains, the memory of bloody skies lingers in conversations and classroom lessons. The red rain of Kerala reminds us that nature can surprise us in everyday events. Clouds, rain, and wind, elements we consider routine, can combine with living organisms and dust to paint the world in unexpected colors. The singing sand dunes in deserts across the world, from the dunes of the Gobi in Mongolia to the sand seas of the Sahara, travelers sometimes hear a strange, haunting sound rising from the sand itself. It's as if the dunes are singing, a low, droning rumble like distant thunder, a deep bass note that swells and fades over several seconds. This phenomenon, known as the singing or booming dunes, has puzzled observers for centuries. How can piles of dry sand produce music? Reports date back at least to the 10th century. Arab desert guides spoke of singing sands near oases, and Marco Polo wrote of strange sounds in the sands of Central Asia. More recently, explorers and scientists have documented booming dunes in places like the Namib Desert, the Mojave, and the Gobi. Visitors climbing the steep slip face of a dune, where sand has built up and slid into a sloping sand sheet, sometimes trigger the sound by sliding down, walking, or even brushing the surface with their hands. The resulting note can last up to a minute, dropping in pitch as the sand settles. Early theories blamed wind whistling through dune ridges or pockets of air trapped between grains acting like tiny organ pipes, but experiments showed that the sound only occurs when the sliding layer of sand is about 2 to 3 centimeters deep, and the grains are clean, dry, and nearly uniform in size. Conditions found in only a few deserts. Mechanical instruments, like wind or trapped air, cannot explain why only certain dunes sing and why the sound's frequency depends on grain size. Modern research points to the grains themselves. When a thin layer of sand slides, each grain bumps against its neighbors, creating friction and tiny vibrations. If the grains are almost perfectly round and coated with a thin layer of silica, found in quartz sand, they act like miniature springs. As the slipping layer moves, grains stick and slip in unison, producing synchronized vibrations that travel through the dune as a surface wave. These surface waves carry the sound up to the dune crest, where it radiates into the air as a low-frequency hum, often around 70 to 105 hertz, about the pitch of a bass guitar. The dune's sloping face acts like a resonant chamber. Its shape amplifies the vibrations, much as the body of a guitar amplifies the string's motion. The deeper the sliding layer and the larger the dune, the louder and lower the boom. Dunes more than 100 meters tall can produce booming sounds you feel as much as hear. Laboratory tests in France and China have replicated the effect. Researchers filled long troughs with ball bearings or silica beads matching natural sand grain sizes. When they created a steady avalanche of beads down an incline, microphones recorded deep, sustained tones matching field observations. By varying the bead size, flow thickness, and incline angle, they confirmed that grain uniformity and layer depth control the sound's pitch and volume. Not all dunes sing, even in deserts known for the phenomenon. Local factors matter. After rare rain, dune sand clumps together, breaking the smooth, round coating that allows grains to slide and vibrate uniformly. Gusty winds can pile fresh, angular sand on top of the slip face, damping the sound. Only after days or weeks of dry weather and wind sorting do the grains become smooth enough to sing again. For desert dwellers, singing dunes carry cultural meaning. In Mongolia, the dunes of Congarine Els are called the singing sands, believed to be the voices of ancestral spirits. In Mali and Mauritania, locals say the dunes hum to warn travelers of coming storms. Today, tourists flock to booming dunes for the rare chance to hear nature's music. Guides teach visitors how to slide down or stamp their feet to make the sands roar, providing an unforgettable audio-visual show. Singing dunes remind us that even the simplest materials, plain grains of sand, can join together to create complex, surprising behavior. They teach about the power of collective motion, individual grains, each too small to notice, vibrating in harmony to produce a deep note that carries for miles. They also warn that delicate conditions, dryness, uniformity, correct slope, are needed for nature's instruments to work. Catatumbo lightning. On the rim of Lake Maracaibo in western Venezuela, storm clouds gather almost every night above the mouth of the Catatumbo River. Then, for up to 10 hours at a time, the sky erupts in near continuous lightning. Hundreds of flashes per hour, dancing across the same patch of clouds. This extraordinary show, known as Catatumbo lightning, can occur 140 to 160 nights a year. Sailors once used it as a natural lighthouse, but scientists still debate exactly why it happens here. The storms form where the Catatumbo River winds through marshes and meets the large, shallow lake. Daytime heat drives warm, moist air upward. At night, cooler breezes from the surrounding mountains converge over the water, forcing air to release rapidly. That rising air cools, forming towering cumulonimbus clouds ripe for electric charge separation. Unlike typical thunderstorms that drift, these clouds stay nearly stationary, continually charged by the river's moisture and local winds. Lightning requires a buildup of opposite charges, positive high in the cloud and negative near the base. When the charge difference exceeds the air's insulating ability, a lightning bolt leaps across a path of ionized air. In Catatumbo, persistent updrafts and humidity continually replenish charge where clouds touch the water's surface, while winds keep the storm anchored in place. The result is a near constant flow of discharge, creating a curtain of light that can be seen up to 400 kilometers away on clear nights. Researchers have studied the phenomenon from boats on the lake, from aircraft, and more recently with satellites. Instruments measure lightning frequency, peak current, and cloud top heights. They've confirmed that Catatumbo storms produce some of the world's highest lightning flash rates, sometimes exceeding 250 flashes per hour. Spectral analysis shows the lightning's color shifts with humidity. Brighter blue-white flashes in wetter air, more orange tints when dust mixes in. Yet several puzzles remain. Why does the phenomenon peak during the rainy season, from April to November, then diminish in drier months? Why do the storms continue so late into the night, long after typical tropical thunderstorms collapse? And why are Catatumbo's clouds so stationary, refusing to drift with prevailing winds? Some climatologists point to the lake's shallow depth and high nutrient content, which encourage microbial activity that releases methane and other gases, possibly influencing cloud electrification. Others focus on topography. The surrounding mountains form a natural bowl, channeling low-level winds into a single convergence zone. That constant feeding of warm, moist air may be unique to this spot. Computer models that include daily temperature cycles, humidity profiles, and wind patterns reproduce stationary storms when they include the lake and river layout. Without that precise geography, the models fail to hold clouds over one location for more than an hour or two. Local reports add another dimension. Fishermen and villagers tell of thunder so constant it sounds like aircraft engines idling. They speak of how the lightning's ultraviolet flashes trigger phosphorescence in the lake's surface algae, making the water glow between strikes. They note that the spectacle attracts thousands of visitors, from scientists to daring tourists who boat onto the lake at night to watch nature's neon show. Catatumbo lightning plays a vital ecological role. Frequent lightning converts nitrogen gas in the air into nitrates, a form plants can use for growth. This natural fertilization enriches soils around the lake and river, supporting the lush wetlands and croplands beyond. Without the lightning's chemical spark, the region's ecosystems might look very different. Imagine standing on a small wooden pier as twilight fades. A gentle breeze carries the humid scent of marsh grass and water lilies. Then, just above the horizon, a flash, bright as a camera bulb, followed by another and another until the sky pulses in a steady rhythm of brilliance. The clouds above shimmer in violet and white, framed by distant mountains. In that electric chorus, let your senses settle into the primal dance of air and water, and as the night hums with charged energy, may your mind drift into a deep, dream-filled rest. The mystery of ice circles. On cold winter days, along slow-moving rivers and sharp bends of streams in Scandinavia, Canada, and parts of the northern United States, people sometimes spot perfect circular disks of ice, smooth-edged, often a meter or more in diameter, slowly rotating in a small whirlpool. These ice circles look impossibly precise, as if cut by an invisible lathe, yet they form naturally, without human intervention or machinery. Let's glide through the calm current and explore how these frozen wheels come to be. Ice circles typically appear in locations where water flows steadily around a bend or drops slightly over a shallow ledge. The flowing water creates a small, stable eddy, a circular current that spins at low speed. When the air temperature falls well below freezing, frail sheets of fragile ice, tiny, slushy crystals, begin to collect on the surface. In the eddy, these ice crystals collide gently, welding together into a thin mat. Over time, the mat drifts into the center of the swirling water. The uniform rotation grinds away any protruding edges, sanding the disk into a nearly perfect circle. At the same time, the continual motion polishes the ice's underside, keeping it roughly level with the waterline. The result is a floating, spinning disk that can persist for days, slowly turning at a typical rate of a few centimeters per second. In laboratory experiments, scientists have reproduced ice disks using a circular tank and controlled currents. They introduce slushy ice crystals to the surface, then generate a gentle vortex. As expected, the ice fragments clump and spin into circular shapes. By measuring the speed of the vortex and disk size, researchers have confirmed that the eddy's angular velocity and the disk's diameter are linked. Larger currents form larger disks, and faster spins yield smaller, denser circles. Field measurements back this up. In one study on the Mistsu River in Norway, cameras and temperature sensors tracked a 1.2-meter ice circle as it formed. Air temperatures hovered around 8 degrees Celsius, and the river current at the eddy core measured just 0.2 meters per second. Over 3 hours, Fragile crystals built up a 3-centimeter thick disk, which then spun steadily for 2 days until it drifted out of the eddy and melted in open water. Why are ice circles so rare? They require a precise combination of factors. 1. Slow, steady current. Too fast, and the ice breaks apart. Too slow, and no stable whirlpool forms. 2. Plentiful phrasal ice water must be supercooled just below freezing before a solid surface forms. Small crystals suspended in the current act as building blocks. 3. Minimal wind and debris. Calm air prevents the fragile disk from tipping or catching leaves and sticks, which would snag and break it. 4. Unobstructed eddy zone. Rocks, logs, or sudden depth changes can destabilize the spinning motion. Because these conditions seldom coincide for long, ice circles remain special treats. Nature's quiet sculptures revealing the interplay of fluid dynamics and freezing physics. Local legends sometimes add a layer of folklore. In parts of Sweden, villagers say ice circles mark the spots where river spirits gather under the moon. In rural Maine, some believe the disks are signposts left by ancient water witches, spinning silently until summer. Scientists, meanwhile, see them as elegant demonstrations of vortices and aggregation processes, with no supernatural help required. Beyond their aesthetic charm, ice circles offer insight into broader phenomena where rotation and aggregation occur. Similar principles govern the formation of pancake ice in polar seas, where small flows jostle and freeze into round shapes under wave action. On a cosmic scale, dust and gas swirl into rings around young stars to form planets. Though far larger and of a different material, these grand disks echo the humble ice circle's formation. Imagine yourself standing on a frosty riverbank at dawn. The air is sharp. Your breath forms clouds. You spot a pale disk drifting at the river's edge. Its surface, glassy and smooth. It turns slowly, eerily silent, carved by invisible hands. You watch as morning light glints off its rim, then feel the gentle pull of the current beneath your boots. In that serene moment, let the ice circle's quiet perfection guide you into peaceful sleep, marveling at how simple forces shape nature's artistry. Starling murmurations. Just after sunset in many parts of Europe and North America, as the sky fades to lavender, you may hear the distant rhythmic chattering of countless birds gathering to roost. Then suddenly, thousands, sometimes millions, of starlings wheel overhead in a single, fluid shape, twisting and folding as if the entire flock were one living, breathing organism. These breathtaking aerial displays are called murmurations, and though we now know a great deal about how they form, they still feel like magic in the dusky air. Starlings are small, dark-plumed songbirds, each no larger than your hand. During the day, they forage for insects and seeds alone or in small groups. But as dusk approaches, flocks begin to assemble at predetermined meeting points, trees, tall streetlights, or rooftops, before launching into the sky. Observers count thousands of birds spiraling up in a dense cloud, then sweeping together in swirls that shift shape every second, a roiling ribbon, a spearhead, a pulsating orb, or even a shifting teardrop. For centuries, people guessed at the cause. Some thought starlings danced to confuse predators. Others believed they perform communal ceremonies. Today, we understand that murmurations offer real benefits. When starlings group tightly, each bird reduces its personal risk of being singled out by a hawk. The ever-changing shape makes it hard for a predator to focus on any one target. Moreover, by watching their neighbors, each bird gains up-to-the-moment information about where to fly next, whether to avoid an obstacle, chase a sudden insect cloud, or respond to an approaching threat. Researchers have studied murmurations with high-speed cameras, GPS trackers, and computer models. Contrary to what you might expect, each starling doesn't monitor the entire flock. No bird can keep track of thousands of individuals. Instead, each one pays attention to about 6 or 7 nearest neighbors, matching their speed and direction almost instantly. This local coordination propagates like ripples in a pond. If one bird veers left, its immediate neighbors copy that movement, and their neighbors copy theirs, until the entire flock shifts in harmony, with delays of just a few hundred milliseconds. Laboratory experiments with groups of robot starlings and simulated agents have confirmed that keeping track of a small number of nearby birds, rather than all of them, produces the same sweeping, coordinated patterns seen in the wild. The key ingredients are simple. Each bird maintains a preferred distance from its neighbors to avoid collisions, aligns its direction of flight with theirs, and adjusts speed to stay within the group. No single bird leads or plans the maneuver. The murmuration emerges from countless split-second decisions, each guided only by local information. Murmurations also help starlings exchange information about food. If a few birds spot an insect swarm, their sudden chase through the flock sends a wave of movement that travels across the murmur, guiding others toward the feast. In this way, murmurations act like living maps, transporting knowledge of abundant feeding grounds quickly and efficiently across thousands of birds. Why do murmurations feel so enchanting to us? Part of it is scale. Watching a mass of feathered bodies twist in unison, reflecting the rosy twilight light, is a visual marvel. Part is sound. The collective murmuring calls of thousands of birds create a soft, rustling roar that rises and falls like the sea. And part is mystery. Although we understand the rules behind the movement, we can't predict exactly how a given flock will swoop and surge next. So each murmuration remains a one-of-a-kind performance. These displays usually last for only 10 to 20 minutes before starlings settle one by one onto roosting branches, filling the tree canopy like living leaves. At daybreak, they launch again, retracing their homeward paths in smaller groups. In winter, murmurations are especially grand, as birds from wide areas gather into larger flocks for warmth and safety. For city dwellers, murmurations offer a moment of wildness amid concrete and streetlights. In rural areas, they signal the changing seasons. Summer's long evenings give way to autumn's cool nights, and the flocks grow larger as winter approaches. Nature centers and bird-watching groups sometimes host murmuration viewings, teaching visitors where to stand for the best perspective and what behavior to expect. Fire rainbows, circumhorizontal arcs. High in the sky, far above ordinary rainbows, you may sometimes glimpse a brilliant band of rainbow colors stretching horizontally like a ribbon beneath a thin, wispy cloud. These fire rainbows, properly called circumhorizontal arcs, look as if the sky itself has caught fire. Though they are bright and colorful, they do not involve flames or heat, only sunlight, ice, and the right angle between them. A circumhorizontal arc appears in high-altitude cirrus clouds, those feathery, ice crystal clouds that drift at 10 kilometers or more above the ground. The crystals in cirrus clouds are typically flat, hexagonal plates, almost like tiny windows in the sky. When the sun is high, at least 58 degrees above the horizon, its light can enter the top face of these flat crystals, pass through them, and exit out a side face. Because the crystal acts like a prism, the light spreads into its component colors: red, orange, yellow, green, blue, indigo, and violet, forming a vivid stripe parallel to the horizon. Not every cirrus cloud produces a fire rainbow. First, the sun must be high enough in the sky, midday in summer for many temperate regions. If the sun is lower, the geometry doesn't work, and the refracted light does not reach observers on the ground. Second, the ice crystals must be uniformly oriented, lying nearly horizontal as they float. If the crystals tilt, the refracted colors smear into faint glows rather than a sharp arc. Finally, the cloud layer needs to be thin enough so that sunlight can shine through cleanly, yet dense enough that many crystals join their colors into a bright band. When all these conditions align, the result is a spectacular, glowing stripe of colors running sometimes across a span of 10 or 20 degrees of sky, much wider than a typical rainbow. The colors are strongest on the inner edge, with reds above and blues below, reversing the order of a normal rainbow. Because the light refracts at a fixed angle through ice, about 46 degrees, the arc always appears at the same distance below the sun, shifting in the sky as the sun moves through the day. Fire rainbows have drawn attention since at least the 19th century. Early photographers struggled to capture them, often overexposing their plates or using filters to tame the glare. Today, smartphones and digital cameras record these arcs more easily, though it still takes a careful eye to spot the delicate colors amid white clouds. Observers often describe the sight as magical, a fleeting promise of wonder hung low beneath the sun. Folklore around fire rainbows varies by region. In some cultures, they were thought to be omens of good fortune, heralding mild weather to come. Others saw them as fiery messages from the gods, or as pathways for spirits dancing across the sky. Modern sky watchers, armed with knowledge of optics, see them as reminders that even the thin air above us can act like a prism, painting the heavens in living color. Beyond their beauty, fire rainbows help scientists study atmospheric conditions. By measuring the brightness and sharpness of circumhorizontal arcs, researchers can estimate ice crystal sizes and orientations in cirrus clouds. That information feeds into weather and climate models, since cirrus clouds influence how much sunlight Earth's atmosphere reflects back into space or traps as heat. To see a fire rainbow, start by watching cirrus clouds on a warm, sunny afternoon when the sun is at least halfway up the skyte. Face away from the sun, scanning the clouds below its position for pale stripes of color. A helpful trick is to use your hand to block the sun's glare. Hold a fist at arm's length to shade your eyes and let the vibrant band stand out against the pale cloud. Remember, though, never look directly at the sun. Always use your hand or a sunshade. Circumhorizontal arcs are just one member of a family of ice crystal halos and arcs that include sundogs, bright spots to the sides of the sun, circular halos, and parhelia. Each requires different crystal shapes and orientations, producing a variety of halos, rings, and arcs that can encircle or flank the sun and moon. Fire rainbows are among the most colorful and eye-catching of these phenomena, yet they appear infrequently enough to feel like special gifts. The Brinacle, underwater icicles of death beneath the frigid seas surrounding Antarctica. A strange ice formation drips downward like a stalactite from a frozen ceiling. Biologists diving beneath the fast ice edge have filmed delicate tubular ice tendrils descending toward the sea floor. When one of these so-called brinicles reaches bottom, it freezes everything in its path. Tube sponges, starfish, and even soft corals, leaving behind a lifeless shaft of white. These chilling structures, aptly nicknamed brinicles or ice stalactites of death, are rare and mysterious, and they teach us surprising lessons about sea ice, salt, and the fragile balance of ocean life. Brinicles form in winter when surface seawater freezes into pack ice. As new ice crystals grow, they expel salt into pockets of brine. This brine becomes extremely cold, down to 20 degrees or lower, and very salty, making it denser than the surrounding seawater. Under the ice, this chilled brine leaks out through cracks or channels and begins to sink, carving a narrow plume as it descends. The super-cold saline flow is so cold that it freezes the less salty seawater it contacts, building a thin sheath of ice around itself. Over a few hours, that sheath lengthens into a delicate tube, sometimes over 2 meters long. Inside the brinicle's icy wall, the salty brine continues to cascade downward. Outside, the tube insulates the flow and keeps it from mixing with warmer water. The result is a self-reinforcing ice conduit. The faster the brine drains, the faster the tube grows. Where conditions are just right, a calm under-ice layer, abundant brine channels in the sea ice, and minimal currents, the brinicle can reach the sea floor at great depth, forming a near-vertical icicle. On the seabed, the brinicle's cold plume spreads out in a thin layer, freezing organisms in its path. Soft creatures, sponges, worms, anemones, can be encased within minutes. Researchers observing brinicles in 2011 near McMurdo Station reported a tiny starfish frozen in place as the tube descended around it. Within a day, the brinicle's growth slows as the brine supply wanes or the tube seals off. Eventually, the structure detaches and either drifts away with currents or melts from the inside as slightly warmer water seeps in. Why are brinicles so rare? They need a precise combination of factors. 1. Thick, continuous sea ice. The ice must be solid enough to trap and concentrate brine, yet cracked or porous, so super cold, brine can escape downward through narrow channels. Tier 2. Stable under ice water. Calm water beneath the ice allows the brine plume to fall straight. Even gentle currents can disperse the brine before the ice sheath forms. 3. Very low temperatures. Air temperatures around 20 degrees C or colder ensure the brine is supercooled enough to freeze seawater on contact. Milder winters rarely produce strong enough brine drainage. 4. Slow growth rates. Brinicles require hours to extend meters. Disturbances, wave action, under ice currents, sudden warming can halt their formation. Because those conditions are fleeting, brinicles have only been filmed and sampled a handful of times. Most reports come from the McMurdo Sound region, where thick, calm ice and well-studied oceanography let scientists anticipate their appearance. Adventurous divers risk the cold and overhead ice to swim near brinicles, filming their graceful yet deadly descent. Brinicles are more than a novelty. They reveal key processes in polar marine systems. The rejected brine influences ocean salinity and density, driving deep water convection that helps regulate global ocean circulation. Understanding brinicle formation sheds light on how sea ice affects freezing and melting cycles, nutrient distribution, and even the release of gases like methane from sediments. Beyond Earth, brinicles hint at what might occur on icy worlds. Jupiter's moon, Europa, and Saturn's moon Enceladus harbor subsurface oceans beneath thick ice shells. If similar brine release processes exist there, they could create ice fingers in alien seas and perhaps concentrate nutrients or chemicals around them, offering niches for hypothetical life. Imagine hovering under a flat, white expanse of pack ice, the only light filtering down through cracks above. You see a slender, glassy tube extending from the ice to the rocky floor far below. Inside its frozen walls, a mysterious river of salt-rich brine flows on, silent, noxious, and mesmerizing. You watch as it traces a path around sea stars and sponges, leaving a frost-white tomb in its wake. In that stark interplay of salt, ice, and life, let your mind marvel at nature's hidden architectures. And as the brinicle's slow dance ends, may you drift into a calm, dreamlike sleep. The green flash at sunset. Have you ever paused at the shore or on a hilltop, watching the sun sink toward the horizon? If you're lucky, at the very last moment, a brief flash of green might flicker across the top edge of the setting sun. This captivating moment, lasting no more than a second or two, is called the green flash. Though it's fleeting, the effect delights observers and reminds us how Earth's atmosphere can bend light in surprising ways. The green flash relies on a simple principle: refraction, or the bending of light as it passes through layers of air at different temperatures. Near the horizon, sunlight travels tangentially through a thick slice of atmosphere. Each layer of air, warmer near the ground and cooler above, acts like a prism, separating sunlight into its component colors. Red light, with its longer wavelength, bends less than blue or green light, which have shorter wavelengths and refract more strongly. As the sun drops, its disk is stretched and smeared by atmospheric refraction. The top rim remains visible slightly longer than the bottom. When the lower edge has disappeared, the final moments can reveal only the highest slice of the solar disk, often tinted green. Sometimes You can even see a faint cyan or turquoise hue before the sun vanishes completely. Several conditions need to align for the green flash to appear. First, you need an unobstructed clear horizon. Over the ocean, a lake, or a flat plain works best. Hills, buildings, or trees will block the last sliver of sun. Second, the air must be relatively stable, with a gentle and uniform temperature gradient. Turbulence blurs the colors into a fleeting glow or removes them entirely. Finally, good visibility is essential. Haze or clouds on the horizon can hide the delicate flash. Observers have described different forms of the green flash. The standard flash, a sharp green spot or line atop the sun's edge, lasting a second or two. The green ray, a vertical beam of green light extending upward from the setting sun, often seen when waves on the water cause the horizon to momentarily dip. The blue flash, when conditions scatter light differently, say if there's dust or moisture, shorter blue wavelengths dominate, producing a brief blue edge instead of green. Despite its beauty, the green flash was long dismissed as myth by many. Early sea captains spoke of greenings in logbooks, but skeptics wrote them off as tricks of the mind or optical illusions. It wasn't until the late 19th century that scientists, armed with photography, captured genuine green flashes and confirmed their reality. Today, digital cameras and smartphones can record them too, provided you use a shade or block the sun's glare. So, automatic exposure doesn't wash out the colors. Watching for a green flash requires patience and careful preparation. About 5 to 10 minutes before sunset, find a clear view of the horizon and keep your eyes low and relaxed. Avoid staring directly at the sun. Use a piece of cardboard or your hand to block the sun's intense glare while leaving the top edge visible. As the disk draws closer to the horizon, stay ready. The flash can appear without warning, so keep your gaze steady. If you miss the first, another may follow in a few days if conditions repeat. Green flashes also occur at sunrise, though they are even rarer. In the morning, the sun's rise is slower and often clouded by morning mist or land disturbances, making a clear flash difficult. Yet desert observers and sailors report morning greens on calm, cool dawns over water. Beyond their aesthetic appeal, green flashes illustrate broader lessons about light and atmosphere. They show how layers of air with tiny temperature differences can act like prisms, bending and separating colors. This principle also underlies phenomena like mirages, where distant objects appear inverted or displaced, and the reddening of the sun at dusk and dawn, when blue light scatters away, leaving reds and oranges. Cultural myths surround the green flash too. Some Pacific Islanders believe the flash marked the opening of a portal to the spirit world. Sailors in the Age of Discovery thought catching the green flash brought good luck, safe passage, or even glimpses of future events. Modern skywatchers treat the flash as a small reward for patience and attentiveness, a reminder that seemingly ordinary moments can hold hidden wonders. Imagine yourself standing on a quiet beach as the sea reflects the sky's golden glow. A gentle breeze carries the scent of salt and the sound of lapping waves. You watch the sun's lower edge touch the water. Then, in an instant, a bright green spark appears and is gone, leaving the sky a momentarily deeper hue before fading into dusk. In that fleeting flash, let your spirits lift, and as twilight settles around you, may you drift peacefully into dreams as colorful and unexpected as the green flash itself. Earthquake lights. Imagine standing on a quiet street as dusk settles when suddenly strange glows, pale blues, purples, or oranges dance in the sky above distant hills. For centuries, people living near fault lines have reported such earthquake lights just before or during seismic events. Though eyewitness accounts stretch back to ancient times, scientists still debate exactly how shifts in Earth's crust can paint the sky with ghostly illuminations. Descriptions of earthquake lights vary. Some observers see streams or balls of light rising from the ground. Others report flashes or shimmering glows among clouds above a quake's epicenter. Reports come from around the world, from Japan's 869 AD Sanriku earthquake, where glowing clouds were noted, to more recent quakes in Italy, California, and Mexico. Typically, lights appear minutes to hours before shaking, though they can linger during and after tremors. Because most sightings occurred before modern instruments, anecdote and legend mingled. Ancient writers described fiery spheres emerging from Earth's crevices as omens of disaster. In rural villages, people spoke of phantom fires lighting up gorges. Skeptics dismissed these tales as folk stories or misperceptions of distant lightning. Yet, as seismology matured in the 20th century, researchers began to collect and compare reports more critically. Three main theories aim to explain earthquake lights. 1. Piezoelectric effect in rocks. Certain minerals, most notably quartz, generate electrical charges when subjected to mechanical stress. In the run-up to an earthquake, shifting tectonic plates bend and fracture rock beneath the surface, potentially squeezing quartz-rich layers. The resulting electrical discharges might ionize air pockets or seep up through cracks, creating sparks or glowing plasmas near the ground. Laboratory experiments have shown stressed quartz can emit tiny flashes of light and electric pulses, hinting at how real faults might do the same. 2. Ionization of air by rock fracture. As rock fractures under stress, it can release charged particles, electrons, and positive ions into surrounding air. These charges can travel along fissures to the surface, where they accelerate and collide with air molecules, producing light. In highly humid conditions, these ionized pockets can form glowing plasmas or corona discharges, appearing as faint halos or bands of light. This model helps explain why lights sometimes flicker or appear as rolling glows rather than sharp bolts. 3. Piezoelectric emissions in Earth's ionosphere. A more exotic idea links fault stress to disturbances high above the ground. Electrical currents generated by stressed crustal rocks may flow along conductive pathways through groundwater, for example, up into the ionosphere, a layer of charged particles beginning about 60 km overhead. There, they interact with the Earth's magnetic field, to produce luminous phenomena akin to auroras, albeit tightly localized over active faults. Satellite measurements in recent earthquakes have detected unusual ionospheric disturbances, lending some support to this view. No single theory yet accounts for every observation. Earthquake lights have appeared in dry deserts, humid tropics, and aftershocks deep underground. Their colors and shapes vary with local geology, humidity, and the magnitude of stress. Some quakes produce no visible lights, while minor tremors sometimes spark brilliant glows. Gathering real-time data is difficult. Lights often flash in remote areas before sensors can be deployed. To improve understanding, scientists have begun combining eyewitness networks, ground-based cameras, and satellite imagery. In Japan, automated sky monitoring stations near active faults record optical and electromagnetic phenomena continuously. In the Pacific Northwest of the United States, seismologists coordinate with photographers and drone pilots to capture any pre-quake glows. Advanced instruments measure the slightest electrical and magnetic fluctuations in rock samples and lab faults, seeking precise links between crack formation and light emissions. Beyond academic curiosity, earthquake lights could one day serve as natural warning signals. If reliable patterns emerge, say certain colors or durations preceding magnitude 6 quakes, monitoring systems might alert communities minutes or even hours in advance. That extra warning could save lives and guide infrastructure shutdowns from trains to gas lines. But until scientists pin down exactly how and when lights arise, they remain charming mysteries on the edge of our knowledge. The Naga fireballs of the Mekong. Every autumn along the banks of Thailand's Mekong River, especially around the city of Nong Khai, locals and tourists gather on the night of the end of Buddhist Lent to witness a remarkable spectacle. As the river's current flows silently under a full moon, glowing orange or red spheres rise from the water's surface, drifting up into the sky before fading out of sight. These Naga fireballs are said to be exhalations of the mythical river serpent, the Naga, blessing those who honor tradition. Yet scientists and skeptics seek natural explanations for this annual light show. What people see. Just after dusk, villagers line wooden boats and riverbank platforms, lanterns in hand, waiting for the first fireballs. At a prearranged signal, often the striking of a gong, hundreds of fiery spheres, each ranging from the size of a ping-pong ball to a large grapefruit, shoot vertically from the river, rising anywhere from 10 to 50 meters above the water. They glow steadily for a second or two before dimming and disappearing. Many observers describe the balls as moving in clusters, rising in quick succession, sometimes following river currents before ascending. Traditional beliefs, local lore links the fireballs to the Naga, a giant benevolent serpent believed to guard the Mekong. According to myth, the Naga family's mating season coincides with the end of the Buddhist rains retreat around October. As Nagai parents awaken their hatchlings, the young serpents breathe out phosphorescent breath that appears as glowing orbs. Villagers light candles and incense to honor the Naga, believing the lights signify protection, fertility, and good harvests to come. Scientific investigations. Skeptical researchers have long sought to demystify the phenomenon. In the 1980s and 90s, teams from Thai universities and the meteorological department set up observation stations along the banks, recording the fireballs with high-speed cameras and measuring their temperature and velocity. They confirmed the lights are real, bright enough to register on infrared sensors, and not reflections of distant fireworks or lanterns. One leading hypothesis centers on combustible gases. Organic matter, decaying plants, and algae in the riverbed can produce methane, phosphine, pH3, and diphosphane, P2H4, from anaerobic bacterial action. These gases, trapped under sediment or in riverbank cavities, may bubble up in concentrated pockets. When released at night, a spark from static electricity, electrical equipment, or even a passing motorboat's ignition could ignite the flammable mixture at the water's surface, creating brief, floating fireballs. Flotation on small rafts of plant debris or algae mats could explain why some balls drift laterally before rising. Laboratory tests support parts of this theory. Experiments mixing methane with small amounts of phosphine have produced self-igniting flames at water-like altitudes with spherical shapes if the mixture remains contained until ignition. However, critics note that phosphine concentrations required for spontaneous ignition are rarely found in natural waters, and the exact spark mechanism remains uncertain. Alternative explanations. Other suggestions include will-o'-the-wisp, ignis fatuus. Similar to swamp fires in European marshes, weak luminescent oxidation of organic compounds, particularly phosphorus, can glow greenish or orange, though this usually occurs at ground level, not rising as spheres. Reflections of distant lantern releases. During festivals, many sky lanterns drift upward. On nights with high participation, hundreds of lanterns might be mistaken for fireballs. But coordinated observations using infrared and ultraviolet cameras have distinguished Naga fireballs from hearth-warmed paper lanterns, noting a sharper brightness and shorter duration. Mineral phosphorescence. Certain minerals in river sediments can emit light when disturbed by bubbles or water flow. Yet natural phosphorescence tends to glow faintly for seconds or minutes, not burst upward, and vanish almost instantly. Skepticism and cultural sensitivity. Because the event carries deep religious and cultural meaning, many locals resist purely mechanical explanations, viewing them as disrespectful to tradition. Farmers and monks both insist that no amount of science can fully account for the fireballs, attributing them to the Naga's goodwill. Indeed, attempts to catch or replicate the phenomenon in daylight have largely failed. Most fireballs appear only on the festival night, in pre-arranged locations where rituals have been performed. The Naga fireballs highlight a common theme in natural phenomena. Cultural narratives often interweave with elusive scientific processes.